Okay, so this is our phases of matter practice. So again, question will come up. What is your interpretation on your page? So the first prompt, draw the particle representation of a gaseous element whose particles are diatomic molecules. So what would you draw if you were to draw a gaseous element whose particles are diatomic molecules? Very nice. Oh, we have some clever people who I see you're getting used to the menu option on the board. You can use it to make squares or circles or things like that. Ooh, I'm liking the people who are trying to convey the motion. Now that's something I didn't mention, but that's something to think about. Artistically, how are these moving and how would you interpret that in that space? Kind of like a cartoon, there's kind of like little zooming. I don't know what you would call that, like a zoom motion. Awesome. Yeah. And I think we're all getting it. Di means two, and atomic means atoms. Atoms are the circles that we draw as our particles. And so my version might, use red. I'll use red for mine, but we're looking at particles fused together. Some people are doing sort of like a zooming. Others are using arrows to show movement. And I'm liking what I'm seeing. These particles sort of span all portions of the container that you've been drawing. And that's exactly right. And that's what we should be thinking of. When we're talking about something gaseous, we want to convey that these particles move freely. They extend through all of the space within their boxes. So if you've drawn something like this, which many of us have, then you are exactly correct when we have a diatomic element. Okay, so that was our first drawing. I'm liking what I'm seeing. How about our second one? Draw the particle representation of a heterogeneous mixture containing a liquid and a solid. So it's very open to interpretation. But there are some key words that represent things that need to be a part of your drawing. So I like it. Again, we're starting with boxes. Now, just as a reminder, I think there is a way I think it's on the menu bar where you could save your drawings. So if you like what you've drawn and you want to keep it, I think there's like a file save option. Okay. Now keep in mind with the particle representation, we want to make sure we can identify individual particles. And by that, I mean sort of, we want to say the smallest speck of this matter should either be an atom or a molecule. So make sure we draw those little circles. Yeah, and I think we're getting it. For solid, I'm seeing a lot of sort of cube-looking shapes of sort of stacked particles. So maybe there's sort of staggered stacking, I don't know. In fact, the solid phase comes in many different sort of flavors. So there are many different ways to show the particle representation of solids. We're going to focus on a specific type of solid called ionic compounds, and those tend to be crystalline. They actually form very intricate geometries, and by that I mean you can get these very delicate snowflake-looking arrangements where it's like little tentacles or appendages coming off. You can get very angled cubes and so forth, or maybe more triangular patterns. But crystalline solids have this sort of array of different sort of geometries that they take. And we'll sort of discover why they do that later. So I'm going to draw two different substances because heterogeneous means a mixture of two different things. So I saw some of us making a mixture of maybe one type of particle, but in two different phases. But as long as its sort of composition is different in some way, it counts. So because it's a liquid, it's a little bit further apart, but the liquid does not extend over the entire box. It only partially fills its box. So we see a heterogeneous mixture like this one. What would be an example of a heterogeneous mixture containing a liquid and a solid? You know, it's always good to sort of have a visual in mind or something in mind to keep that, sort of keep something in your back pocket. Maybe something every day. An example when you have a mixture of a liquid and a solid and they don't fully mix. Oh, we have a suggestion in the chat, sugar water. So sugar water, actually sugar is pretty soluble in water. So it would tend to dissolve completely. And so if something dissolves in water, it tends to be a homogeneous mixture. Okay, so salad dressing is an interesting one. I guess it would depend on the type of salad dressing. If it's something, I'm trying to think of the most liquidy, like a vinaigrette, you know, the oil and vinegar. And if you were to, so oil and vinegar by itself would be more of a liquid heterogeneous mixture. But if there were actual particles that you could see in it, like maybe, yeah, like the pepper, like, what else goes in salad dressing? I don't know. You know, whatever ingredients, solid ingredients that you see there, then yeah, exactly. If you just put a paperclip in water, then yeah, I guess that would count as a heterogeneous mixture. Iced water would count technically, even though it's more of a technicality than one that we would go to, but it's two distinct phases of the same substance, so that would count. And then something like if we had ice cubes in any drink, we're seeing iced tea. There would be an example of one. Yeah. So as long as we're on the same page, that's the important thing about classifying matter, so that we can have these conversations and be able to understand each other. Okay. And of course, at any point, yeah, please keep those questions coming about the topics at hand. How about the next one? Draw the particle representation of a homogeneous mixture of a gaseous element and a gaseous compound. Mm-hmm. And don't forget, you can use color to try to differentiate things. In this example, there definitely should be at least two types of circles, whether they in some way should be different from each other. So let's remind ourselves on the technicalities of what an element is versus a compound element. So what is the common theme for elements? Elements have to be what? Oh. Substance whose particles have one kind of atom. And I'll emphasize only. So I'm seeing a lot of different examples of elements here. So I see the classic monatomic element. So it's just a single atom. We have diatomic elements. Some people are being fancy with the triatomic. But the key theme is that for something to be an element, its particle can only have one kind of atom. So notice in all of these examples that I'm showing here, while it may be made out of more than one atom, the atoms that it's made of are all the same. So that means that these are all three examples of elements. Whereas what's a compound? Particles made of at least two different atoms. In other words, different elements. Yeah. So we could have, and just to show an example, a few of you, I think, had this as your example. Yeah, a few of you did. Here we can have a diatomic gaseous, what would this one be? Element. And I'll pick a different color. I'll just use black. And then this that I'm using the black marker for, this would be diatomic compound. So notice how similar they are, but there's a key difference. The element, the particles all have the same kind of atom, but a compound, they need to be at least, there needs to be a difference somewhere. So in this case, this particle is a molecule made of two atoms of different elements. And that's one of the key differences between compounds and elements. The major sort of division is that the compound has two or more elements within its particles, whereas the element only has one type of particle, in this case, atom. All right. Confusing, not so confusing, good, bad? Let me know. Stop me if something comes up. I'm loving the colors. Some of us are using lots of flashing. How interesting. How many colors are on the whiteboard? I'm trying to toggle my whiteboard. Because I'm seeing people use the same 2 colors, and I'm wondering, did you guys do that by accident, or was there some kind of... It's a fascinating question. Okay, I digress. Let me go back. But what's funny is that a few of you used the exact same color combination out of all of the colors that are possible. That's kind of funny. Or maybe it's just funny to me. But okay, let's go to the next one. Draw the particle representation of 2 different compounds made with the same 2 elements. So now it's like, wow, how do we draw the line there? Whoa, a lot of circles appear. Mm-hmm. Yeah, I'm actually... Now remember, to be an example, so we need to first draw one compound that is made out of 2. So give me the particle of a compound made out of 2 elements. So for example, a compound must be made of at least 2 atoms, and they have to be different. So here would be an example of a compound. You know, I didn't tell you what phase or anything, so we can just stop at a few. Now, what makes a compound different from another is that the combination of these atoms has to be distinct. So perhaps we will use the same black circle and white circle in my case, but instead we'll make it triatomic. So this would be, these both would be compounds because their particles are made of 2 different elements, but they are distinct compounds. They're different from each other because the quantities of each are different. So this could be an actual, for example, this is a sort of demonstrating an actual compound. Carbon monoxide actually looks like this. And perhaps you guessed it, carbon dioxide looks like that. But they are distinct substances. And actually, I didn't mean for this to happen, but this is actually a good talking point about the difference one atom can make in a substance. So for those of us familiar with these substances, carbon monoxide is deadly. It's a gas that can cause damage to your respiratory system. And so there are things called, like carbon monoxide detectors, just because it's so dangerous that much like a fire alarm, we want carbon monoxide alarms because those carbon monoxide can leak into homes from various sources. But carbon dioxide is something that we're breathing right now. And it's the difference between one atom. But we'll talk about how the atoms that come together to make the molecules actually impact the properties of that matter. So we'll get a little bit into that. To fully understand why carbon monoxide is bad for us, you'll have to take Chem 1B, or just ask me afterwards and we can chat about it. But yeah, so the difference is these are both compounds, but they're different compounds. So two compounds made with the same two elements. So, and just to reiterate, it's because this is a 1-to-1 ratio of atoms in this compound. This is a 1-to-2 ratio. Oh, I forgot. Now I wanted to segue into the phase diagram stuff. So this will require some axes. So I've drawn some for myself, but it's completely blank. What I'd like us to do is sketch the phase diagram of a substance with a normal melting point of 35 degrees Celsius and a normal boiling point of 55 degrees Celsius. So this is about reminding ourselves, what do phase diagrams look like? And the best way to understand them is to be able to recreate them yourself confidently. And this is our whiteboard in case anyone needs it one more time. Okay, I see us starting to get our axes down. Now let's just remind ourselves what goes into a phase diagram. These are the conditions in which we can figure out the phase of matter for a substance. So we have an x-axis and a y-axis. What goes on the x-axis? Oh, this is going to be temperature in degrees C, in this case. And then what goes on the y? Pressure. What's our unit of pressure? We'll talk about it more tomorrow. 18. Oh, that actually reminds me. I have a pre-lecture for tomorrow. So it actually goes into what is pressure. So you can know about pressure before the lecture. So the variable for pressure is P and the temperature is T. So, you know, if you've seen it, I think maybe in the lecture I might do that. Oh, and by the way, temperature is capital T. Lowercase t is actually used for time in math. And while it's not too big of a deal, if you're going to go on to say physics or Chem 1B, it gets confusing if you don't remember that capital T stands for temperature, lowercase t stands for time. So remember, this is our graph that looks like a Y shape, kind of like that. So I see some of us are drawing the heating curve that we learned today. So remember, so this is important, and this is something that's really important to know before we start getting homeworks on it and so forth, is that the phase diagram is the one that looks like a Y. The heating curve is the one that looks like a zigzag. So if we're not So if we might want to make a few adjustments for some of us. Normal means one of two things, either 1 atmosphere of pressure or 760 millimeters of mercury. So wherever we want, because I'm not being picky, we're just sketching, we'll put the 1 here since it is in atmospheres. And we're going to go across. And so all that I'm interested in is that you labeled the part where it crosses the correct place. This is going to be the melting. This is going to be the boiling. So this is going to be at 35. Well, actually, yeah. This is going to be 55. Perfect. So what does this tell us? It tells us that under normal pressure, we cross from solid to liquid. Here's where we cross. We cross at 35 degrees normally at 1 atmosphere. Normally, at 1 atmosphere, we cross from liquid to gas. We boil at 55. So that's how this one looks. Any questions? All right. How about this one? You already have one written, but if you need to sort of clear it and try again, that's fine. Sketch a phase diagram. Use an arrow to show the substance undergoing fusion from an initial point to a final point. And bonus, draw 2 more arrows, that require different kinds of changes to P and T. So we've already concluded what the phase diagram looks like. It's kind of like that, and that, and that. Now, an arrow that is showing a starting point going to a final point that involves fusion and I'm not picky, any line that would indicate start to finish has gone through fusion is fine. So I'll try one myself. How about going from a starting point here to here? How do we agree with that? So this might be a good time to remind ourselves, fusion is melting. It's the fancy word for it that we want to know. Now, for my particular line, what did we have to do to the substance to make it undergo fusion? What are we doing to its T and or its P?
Raising the temperature.
We are raising the temperature, exactly. So my question to you is, can you draw me a different way to go through fusion that requires changing P and or T without with a different kind of transformation? In other words, draw a different arrow. Maybe I'll draw my own arrow. Oh, I should use that color. It's this one. Oh, maybe I'll label what we did. And again, we know that because we're going this way. I don't know if you guys mind if I call you out, but I want to be like, good job. But I want to like respect your privacy, you know? Yep. I am seeing some. So I'm going to recreate some that I'm seeing on here because they're absolutely correct. Oh, except I want to use. We have one that looks like this. Now, if I do this transformation, I'm crossing from solid to liquid. I am undergoing fusion. What am I doing to my substance that's different in this line than just the red line where I raise the temperature? This is raise the temperature and the pressure. So how do we know that we raised the temperature? Because we've moved further to the right, but we've also raised the pressure. So in this way, this melting is different from this melting because you can melt something by changing the temperature. That's going horizontally across, but you can also melt something by raising the temperature and the pressure if you go like this. So this is how we can sort of adjust our conditions so that we can get to the phase that we want. Or another person, another right answer, did this, a vertical line. This vertical line is also going through fusion. We're crossing from solid to liquid, though what are we doing that's different from the others?
It looks like you're keeping the same temperature, but putting more pressure on it.
Keeping the temperature the same, we're definitely changing the pressure. If we're starting at the top and moving towards the middle, if we're looking at our axes, we'd probably say that we're lowering the pressure. Lower P. So in this case, we would be lowering the pressure would cause us to turn this solid into a liquid. So absolutely, there are many different ways we can do this. It's important that we're able to read the graphs correctly. So I encourage you to take a look at the graphs in the textbook, in the module, and be comfortable saying, well, if I'm looking at positions going left, right, what variable is changing? And going up, down, what variable is changing? One thing to note is that by looking at how we can move, we see that there are different ways to a desired outcome. If we want to melt a solid, according to this phase diagram, there are specific conditions that we could change to get it. And there are special conditions where we can lower the pressure without having to raise the temperature and still get to a solid, or sorry, still get to a liquid. Now, there are some positions on the phase diagram where you can't do that. For example, if I'm way up here, lowering the pressure actually won't turn me into a liquid. It would eventually turn me into a gas, not a liquid. So, I mean, there are limitations to what you could do, but with a phase diagram, we can sort of figure out what possible strategies there are to change the state of matter. And that's pretty cool, I think. So I mentioned there's a video that I like about the triple point. So I wanted to show that video to sort of illustrate what the triple point looks like. Oh no. Oh shoot. Oh goodness. Okay, so apparently it's not working. Okay, strategy, changing strategies. What I'm gonna do is look for it really quickly. Okay, if you haven't seen this already, it's worth taking a moment to see. So I'm gonna post it in the chat. So this should be, let's double check. This should be the link to it. So let me just, yep. That's the link to it. So I encourage you to just take a look. So for those of us who haven't seen what a triple point looks like, I mentioned on the phase diagram that the place where all of our lines meet, that's the triple point. That's where all three phases of matter exist because all three sections of the phase diagram collide with each other. And so, you know, I'll kind of stall and sort of go slowly because it really is cool to sort of take a look at how the triple point sort of manifests. So this person takes water and then starts adjusting the pressure so that their position on the phase diagram is exactly at the center where those three lines meet. And it's just really cool to look at. And this lab is from UC Santa Cruz. Please, on a scale of 1 to 10, let me know how cool you think this is. Woohoo. Yeah, I think it's amazing to see ice bubbling because it's boiling, right? And then you see it start to come off as liquid, and then bubbles get trapped in the liquid because it's starting to freeze again. So you're seeing all three phases of matter kind of cycle through one another. And as long as the experimenter keeps those conditions, so, you know, you have to have a thermostat, you know, to make sure we keep the same temperature. And they say it's keep the water just above its freezing point, so 0.1 Celsius. And then the pressure has to be extremely low. I think it said 0.0006 or something atmospheres. So you'll need a vacuum to suck out most of the air. But when you do that, you see this incredible place where all three phases exist with one another. So you have boiling ice and solidifying gas and everything in the middle. So I thought that was pretty cool. I'm going to add it to the module if it's not already there. But hopefully I've excited you that with the idea that phases are fun. And technically, this happens without any other outside disturbance. It's because the conditions are such that the particles have sort of are equally favoring the three different phases of matter. There's only one condition in which all three phases of matter are doing this. If it's done correctly, it's not due to any experiment error, or there might be fluctuations in things. It's a theoretical limit in a sense, so it's very hard to get perfectly. But in theory, without any other outside disturbances, all three phases of matter are going to exist together at the triple point. Some triple points are easier to get to than others. So in this case, we saw, according to the beginning, you need to get water to 0.1 degrees Celsius, so almost freezing point. And then you have to pump out almost all of the air in the container to get such a low pressure. So there we have that. Just wanted to add a little excitement to all this. Okay, the rest of this is going to be, I just wanted to have us do a couple more calculation examples so that you have that in your notes, you have a video of it. And particularly on the mole idea, which we didn't have a lot of time to spend on, but it falls under the umbrella of dimensional analysis, which itself is important to study for the end of the week. But then, you know, we'll also talk more about moles, and that's going to be a big topic moving on even from right now. So it's important. So if you don't have your calculators out, get your calculators out, because I want to make sure we can practice typing things in and getting them to the right answer. So let's try a calculation question. Get your calculator ready. The population of Earth is currently 7.549 times 10 to the 9, which means billion people. How many moles of people are on Earth? So moles as in the unit, not that I'm calling people animals. Sometimes I crack myself up. All right. So let's remind ourselves, and reminder, by the third quiz, you do need to know what a mole is. So let's do our given. Oh. Desired. We want to turn 7.549 times 10 to the 9 people into mole people. And remember, it's kind of silly, but the abbreviation for mole is just drop the E. So we take our number that we're going to convert, and we're going to set up a conversion factor. I'm going to give myself plenty of room. So what needs to be on the bottom? Well, our unit, in the case of things like moles, our unit is whatever we're counting. So we're counting people. So people goes on the bottom. And then the unit we want, which is moles of people, goes on the top. So if it's at all confusing what numbers to put where, remember, my advice is to go back to thinking of it like dozen, the chemist's dozen. A dozen means 12 things. A mole is our dozen. So it's going to be 1 mole is 6.022 times 10 to the 23 people. So what does that come out to? Actually, I don't know myself, so I have to type it in right now. Okay. Now, we have 4 sig figs and 4 sig figs. So it's going to be 1.254 times 10 to the minus 14 moles of people. How do we interpret this? What does it mean to have 1.254 times 10 to the minus 14 moles of people? Well, what we're saying is that we're trying to group people into our version of a dozen, right? All the people on the planet. What this number is telling us is that the size of our grouping is such that all of the people on the planet don't even fit into a fraction, into a very large fraction of this sort of sized grouping. So it's like saying I have a fraction of a dozen, I'm having a fraction of a mole, except this time what we're saying is the size of a mole is so big that all the people on the planet don't fit very, very much at all into the size that we're talking about. So what we would say is that probably it's not a good idea to measure people in moles because we use very, very strange numbers in that case. But this would be our answer. A tiny, tiny fraction of a mole. But in contrast, a helium balloon, helium is He abbreviated, contains approximately 0.25 moles of helium atoms. How many total helium atoms are in the balloon? So this time we have a balloon, and it has helium atoms. So we're going to say given, desired. And what do we want to do? We want to take 0.25 moles of helium and turn it into total helium atoms. Now, this is another example where the wording gets a little bit odd when it comes to this. So let's make sure we set up the units in the fraction so we know we're putting them in the right place. And let's practice saying it out loud. I know I can't hear you if you don't have the microphone on, but let's practice, do it to yourself, but saying the chemist's dozen, right? the mole is the chemist's dozen. So think of the word dozen and how you would turn that into a fraction. Where does the 12 go? Where does the 1 go? And do the same thing to the helium. So some of you might want to reconsider how you've written 0.25 moles of He. Now we want mole on the bottom, and we want atoms because that's what we're counting on the top. So 1 dozen is 12 things. So how are we going to word it? The mole is our version of a dozen. 1 mole is 6.022 times 10 to the 23 things. So some of you might want to consider flipping your fraction. You have the units right, but we want to make sure we recite what this means. 1 mole is like 1 dozen. So 12 things is like the 6.022 times 10 to 23 things. That's how we associate the two. So that means we're going to multiply 0.25 times 6.022 times 10 to the 23. Because this is 2 sig figs, our answer is going to be 1.5 times 10 to the 23 atoms of helium. So that would be our answer. So this is just to compare the difference. A balloon of helium contains about 1.5 times 10 to the 23. So remember, that means moving the decimal place 23 times. So this many helium atoms is a an astronomically huge number. Compare that to all the people on the Earth. That's barely a drop in the bucket of what a mole is. So there are far more helium particles in a balloon by a lot. There are far more helium particles than there are people on Earth. So something to think about. It's definitely something that's shocking when you kind of think about all of the people are don't even add up to the amount of particles in a balloon. And yet here we are. Impressive. Okay, one last one to sort of practice our mole calculation. 1 mole of water weighs 18.02 grams. How many water molecules are in a glass containing 50 grams of water? Now this one's a little bit different because it throws a little bit of a curveball. There's a bit more interpretation we'll have to think about. Now, the way some of you are interpreting the information, I can tell you've taken a chemistry class before. You kind of know what I'm doing in this question, but that's okay because we're going to be talking about it at length next week. So yeah, let's do our given, our desired. We want how many molecules? So we want molecules of water. Now we have an interesting one. We have 1 mole of water is 18.02 grams. And maybe I'll say water. And we have, maybe I'll draw it too. We have a class that's 50 grams. So in this case, can we see the connection or connections? Remember, one thing that I emphasize is check the units and what they're measuring and see if you can see patterns or relationships. Yep. Now we want to be careful when so I see a lot of us interpreting this as a conversion factor, and it is because it's a relationship between 2 things. Remember, we look for things like this equals that. That's a relationship. We want to be careful that we put it as 18.02 grams over a mole of water. Grams of water. I would say when you're starting to do your math, avoid doing the slash line because the slash line sort of messes with how you perceive things. For example, I'm going to show you an example of a typo I see students making in previous years. If you have like grams per, in this case, we have grams per mole, there's a tendency to think that that means mole has to go there because literally the line you wrote in your paper has the mole on the topmost line. But that's not actually true. It's actually grams per mole means that we need it to look like this. So that's an example of a mistake that I see students make. we're going to want to make sure to rectify that. I'm just demonstrating the conversion factor. I'm not necessarily saying that's how it's supposed to look in the answer. But what I will say is that I'm demonstrating just a general idea of what you want to watch out for. Don't do it like this, because notice you're doing it, you're not going to get the cancellation you think you're going to get. Write your fraction like this, and then you'll see if moles is on the bottom of the slash, you need moles on the top of the slash. But I'm not saying that that's how you do this problem. I'm just saying that that's something to look out for. But I digress. Let's maybe actually do this problem and see what we have. So this is considered a conversion factor. So I would consider this my given. I always like to start with the number that's not the conversion factor. And usually that's the most straightforward way to go, in my opinion. So I'm going to start with, I have 50 grams of water, and I want to convert it to how many water molecules there are. So this is 50 grams of water, and I'm going to need, oh, look, I have grams here. Grams of water to moles of water. The number is 18.02 grams per, and we could put a 1 there for the 1 mole. So there we go. We're going to cancel. And now we want to go from moles to molecules. Oh, we were just talking about the conversion. A mole is just a grouping of items. So a mole is equal to however many things we're counting. So a mole of water to, now this is where you also have to be careful. You want to really spell out the word, molecules of water. That way it doesn't get as confusing, because notice these words look very similar. So be careful. Make sure you spell it out completely. This is where we realize a dozen is 12 things. So a mole is 6.022 times 10 to the 23 things. So that's going to be our math. We're going to take the 50. We are going to divide it by 18.02. And we're going to take that answer and multiply it by 6.022 times 10 to the 23. With 3 sig figs and 4 sig figs, we're going to round to 3. So I take 1.67 times 10 to the 24 molecules of water. And that's how many water molecules there are in a glass of water. Whew, we did it. How does that feel? Is it starting to feel better? And then just a reminder, if your scientific notation doesn't look like this, say the decimal place is in the wrong spot, you're just going to want to move it one more place and then change the exponent. You want it to be 1 digit and then the decimal point always. So if you got something like 167 times 10 to the 22, you're going to want to move it over. I love when people ask me, do I have harder problems of these? Yes, I do. And in fact, we're going to cover the harder versions of these problems in next week. And with that will come another set of practice sheets on Canvas. For now, we're just kind of practicing counting things with the idea of a mole. So more is yet to come. In fact, this problem is me trying to sneak in a sort of question that comes up later in the class, comes up next week, just to see how we fare about this. The idea is dimensional analysis, making sure we set things up so that they cancel. All right. Feeling good, feeling hungry, feeling befuddled? Let me know. Scale of 1 to 10. How happy are we about this information? Oh, I see happy face. Yay. Awesome. Yeah, the work is looking good. Oh, I'm saying, oh no. If your face does not reflect what you want to feel, then please talk to me, and we can work on more. I understand the sentiment of just wanting more practice, especially on this. And so let me start by saying this last question is something that we're not going to focus on until later. It was just meant to see like how do we do with dimensional analysis. More like this question. Think more like this question is something you might see on the next coming relevant quiz, which is quiz 3, or this one. Oh no, so yeah. Whichever quiz. I honestly am not sure at this point. So yeah, keep that in mind. We're gonna start slow with this topic. Can we count using the mole? Okay, with that, I'm gonna go ahead and stop the recording. It's perfect timing because the cat is making all sorts of noise. So let's go ahead and stop.